Welcome. If you're looking to move from just, using large language models to actually engineering them, then you are in exactly the right place. This is your deep dive on how to build predictable, production-grade AI applications. So let's just get right to the core of it, shall we? This is the fundamental challenge for every single software engineer moving into AI. Your whole career has been built on predictable, deterministic logic. If this, then that. But LLMs? They're probabilistic. So how in the world do you impose order on that chaos? How do you take control? Well, that is exactly what we're going to break down. Here's our game plan. First, we'll nail down what prompt engineering actually is. Then we'll get hands-on with the 3 core techniques you need to control a model's behavior. After that, we're talking production realities, optimizing for speed and cost, and tuning for creativity. And finally, we'll wrap it all up into a straightforward, actionable playbook that you can start using on your projects like today. Okay, let's dive right in. Before we can even think about controlling the model, we have to understand the discipline we're using. And really, you can think of this as learning the syntax and grammar for a totally new kind of programming. So what are we really talking about here? At its heart, prompt engineering is all about this. The power of an LLM is unlocked by the quality of your communication. The model's performance depends almost entirely on how you ask. As an engineer, you should think of the prompt as your API call. Learning to engineer that prompt is like learning how to pass the right parameters to get a reliable, non-buggy response every single time. Now, let's get into your foundational toolkit. These are the 3 core techniques that will give you direct, hands-on control over the model's behavior. Honestly, mastering these is non-negotiable for any serious AI engineer. First up is zero-shot prompting. This is your baseline. It's the first and simplest tool in your toolbox. You're giving a direct command without any examples, and you're just relying on the model's massive pre-training to figure out what you mean. It's the most straightforward approach, period. A classic zero-shot prompt like this works because the model has already learned the connections between concepts like JSON, beginner, and simple terms from the mountain of data it was trained on. You're basically leveraging its built-in knowledge to get a direct answer without any hand-holding. So, when do you actually reach for this tool? For any of these low-complexity jobs. If you need a quick summary, a simple definition, a direct answer, always start with a zero-shot prompt. It's just the most efficient way to get straightforward things done. Okay, but what happens when direct orders aren't enough? That's when you escalate to few-shot prompting. The strategy here shifts from just telling the model what to do to showing it. By providing just a few examples, you tap into the model's incredible in-context learning ability, teaching it the exact pattern you want it to follow, right on the fly. And this example just illustrates the idea perfectly. You're providing a crystal-clear input-output pattern. You aren't just telling it to be polite. You're showing it exactly what polite looks like in this specific context. The model sees the pattern, mimics it for your new input, and boom, you get a highly predictable result. This is the tool you're going to reach for when precision is absolutely non-negotiable. If you need perfectly structured JSON every time, or a very specific tone of voice, or if you need to correct a model that's just being inconsistent, few-shot prompting is your go-to for enforcing that structure and style. All right, for our 3rd core technique, we're bringing out the heavy machinery, chain of thought prompting. For complex problems, things that involve logic or math or multiple steps, you can't just ask for the final answer. You have to explicitly instruct the model to think through the problem, step by step, which activates its internal reasoning pathways. The absolute magic phrase here is step by step. By forcing the model to show its work, you dramatically reduce the chance of it making a mistake in logic or calculation. It's really the same as asking a junior developer to write out their pseudocode before they start writing the actual function. Now, what's really cool here is that we're basically visualizing the process you just kicked off inside the model. It's not just jumping to an answer. It is methodically breaking down the problem, recalling the formula it needs, plugging in the values, doing the math, and then stating the final answer. This structured thinking is what gets you accurate results on complex tasks. All right, we've covered how to get the right answer. Now, let's shift gears and talk about the engineering realities of production, getting that answer efficiently. This is where we go from just designing prompts to really optimizing the entire system with a laser focus on speed and cost. Your first and honestly most powerful lever for optimization is prompt caching. The idea is so simple. Don't pay to reprocess work the model has already done. For any application that has a long system prompt or repeated context, like a chatbot's conversation history, caching is a must. It's a non-negotiable tool that can slash your costs by up to 70%. And you've got two main ways to do this. There's implicit caching, which is done automatically by some providers. It's zero setup, a totally free win. But for more control, especially in complex systems like a RAG pipeline or a chatbot, you'll want to implement explicit caching on your side, using standard tools like Redis or different framework layers. Next up, token budgeting. And you have to remember this. You pay for every single token, both in your prompt and in the model's response. Managing your token count isn't some afterthought. It is a core engineering discipline that can easily cut your operational costs by more than half. This means writing concise instructions, summarizing long documents before you feed them in as context, and always setting a max tokens limit on the output. Okay, now let's look at the parameters that let you really fine-tune the model's output. Think of these as the creativity and predictability dials. They let you shape the texture of the response, moving it from rigidly factual all the way to wildly creative. The most important dial you're going to play with is temperature. And the rule of thumb for engineers is super simple. When you need factual, deterministic output, for things like code generation or math problems, you turn the temperature way down. When you need brainstorming or some creative marketing copy, you crank it up. Now, top P, or nucleus sampling, is another way to control randomness. While temperature adjusts the odds for all possible next words, top P creates a smaller pool of just the most likely words to choose from. For example, a top P of 0.9 means the model only considers the most probable words that add up to 90% of the likelihood. For most production apps, a value somewhere between 0.8 and 0.95 will give you reliable, natural-sounding results. All right, let's bring it all home. We've covered a lot. Core techniques, optimization strategies, tuning parameters. Now we're going to pull it all together into a clear, actionable playbook that you can take back to your team. This is your standard operating procedure. For any simple task, you start with zero shot. If that's not cutting it or the problem is more complex, you escalate to chain of thought. If you need a specific format or style, you use few shot. And at every single stage, you build with optimization in mind. Use caching and budget your tokens. Finally, for production-grade reliability, tune your parameters, keep the temperature low, and enforce output constraints like JSON. This is how you build faster, cheaper, and smarter LLM applications. Look, this isn't just theory, right? This is your playbook. So here is your first assignment. Take these techniques, this structured approach to controlling a probabilistic system, and apply them to a real engineering challenge that you are facing right now. The control is now in your hands.